Sodium hydroxide is a strong base. It will completely dissociate into sodium and hydroxide. I get 0.03, I get 0.03. Do I care about the sodium? I don't care less about sodium. What do I care about? The hydroxide, because the hydroxide makes the solution base. What they want the pH. Watch this. I need to find the hydrogen ion. Hydrogen ion times hydroxide should be equal to what? Remind me, please. 10 to the negative 14. I know the hydroxide. Can you figure out the hydrogen? Use your calculator and figure out the hydrogen ion, please. When I say 0.03, how many sig fig is that? 0.03, how many sig fig? 2 sig fig. I need to end up with 2 sig fig. Do I have 2 sig fig here? Yeah. Ready for find the pH? Have you learned it yet? Negative what? I forgot. No. Negative log? Yes. Take 1 divided by that number, and that's what you get. Do you have a calculator? Use a calculator. 1 times 10 to the negative 14 divided by 0.03. What do you get? I'm waiting for you here. Confirm those numbers. Yes, you got it? Yeah? So now, log the hydrogen ion. 3.3, 10 to the negative 13. Do not break it into A and B. Use your calculator and find out negative log, open parentheses, 3.3 times 10 to the negative 13. Are you okay?
Yeah.
This is chemistry 111.
Where is the house science building?
I cannot describe it here. Ask somebody outside. I'm sure you're going to find someone to help you. Did you find it, you young people? I got 12.48. How many sig fig is that? How many? 2 sig fig. Teacher, I see four digits. Why don't you count that 12? That 12 is the remainder of what? The 13, the exponent. So convince yourself we have 2 sig fig. Can we work it backward? If I give you the pH, can you give me the hydrogen ion? Let's work it backward. That's example 3. Example 3. I'll wait for you guys. I'll show you how to work it backward. Shall we move on? Go to example 3. What is the pH? Is it 3 or example 4? What is the hydrogen ion when the pH is 12.7? Is this acidic or basic? First tell me. Basic. Thank you. How many sig fig?
1.
Can you see that? Whatever you understand right now, please go home one lecture, they forget about it, they come back the following week, say, what was it? What do you do? Well, I don't know what kind of calculator you have. You can punch 12.7. You can punch. Can you see that? The switch sign, again, 12.7, switch the sign to negative. You have a button, they say 90 seconds, and you say long. And people say, teacher, my calculator is not like that. How about if you go second, and you punch log, you punch switch sign, you punch 12.7. And people say, teacher, how about, I'm showing you different things, guys. Teacher, how about if I just enter 10 to the power negative 12.7? You can do that too. And that will give you the hydrogen atom. Which one worked for you? The one that worked for you, write it down. You remember now? Wait until the exam comes, and during the exam, you stick that calculator in my face, say, teacher, show me how to use my calculator. I can't, guys, I'm showing you now. Anybody has the first method? No? One person, 2, 3. Anybody has the second method? Nobody, one person? Anybody has the third method? Yeah, lots of people. Okay. Remember, I want you to use the calculator you bring to the exam. Use the calculator. You should have gotten 10 to a negative 13 m. How many sig fig? 1 sig fig. You should have gotten 2 times 10 to a negative 13. Would you kindly write the answer for number 3 so you can try it at home? Remind me again, what is exam number 3? I have some news for you. Exam number 4 will come very shortly after exam number 3. Unit number 4 is very small. All right, let's go to page 5. Equilibrium. Don't talk, please. Equilibrium is not a new subject for us. We talked about equilibrium before. Let me remind you. If you have water, water tends to evaporate. If you have a question, ask me afterward, please. If you have water, water tends to evaporate. Gas. The number of particles in the vapor is constant. Are they the same particles? No. The particles in the vapor go down, and particles from the liquid replace them. We call that dynamic equilibrium. Dynamic means there is motion. What we have here is vapor. Another situation, we use dynamic equilibrium. We have a saturated solution, let's say sugar solution. So saturated The number of particles dissolved is constant. Are they the same particles? No. The particles in the solution go down as solid, and particles from the solid go up in the solution. And again, we have dynamic equilibrium. Dynamic means motion. They are not the same particles. So here I have saturated solution. And here I have just liquid evaporating. So yes, we are familiar with dynamic equilibrium. We're not going to talk about liquids or solutions. We're going to talk about chemical reaction. We call that chemical equilibrium. And chemical equilibrium that we're going to talk about is also dynamic equilibrium. Watch this. You put nitrogen gas, you mix it with hydrogen gas. Are you there? They react a little bit and form ammonia. But guess what? The ammonia is not very stable. It decomposes back into nitrogen and hydrogen. You see that? Reaction does not go to completion. Let me remind you what we mean completion. Completion means all the reactants to react and I only have products. No, I don't have that situation. What do I have? I have a mixture of everything. Hydrogen gas, nitrogen gas, ammonia gas, they are all sitting together in the same container. These two forming ammonia, the ammonia decomposing, forming these two. They're going back and forth. Is the motion going on? Yes. Motion means what? Dynamic. When the reaction reaches dynamic equilibrium, I want to measure the relative concentration of ammonia to the nitrogen and hydrogen. We express that by a constant, and we call it equilibrium constant. I'll tell you more about it in a second. The equilibrium constant tells me the relationship between the amount of ammonia and the amount of nitrogen and hydrogen. We express it in this form. We put what we have on the right. Always, we put it on the top. What we have on the left, always, we put it at the bottom. Have you noticed I'm raising the concentration to a number? And this number equals to what? The coefficient. Have you noticed I raised the hydrogen to 3? And the 3 is equal to what? The coefficient. So what does the equilibrium constant represent? It tells me when the reaction reaches equilibrium, do I have more ammonia or do I have more nitrogen and hydrogen? If K is very large, what does this tell me? Which one is large? The ammonia is large or nitrogen and hydrogen is big amount? Which one?
Ammonia.
Ammonia is large. Got that? How about if K is very small, 10 to a negative 15? What does this tell me? What is small, the top or the bottom is small?
At the top.
So if you want to know the relative amount of the ammonia to the nitrogen and hydrogen, express it as equilibrium constant, and we call it big letter K. People put small k and say, you're kidding me, I take all points. Teacher, does it make a difference? Yes. Large K. we added nitrogen and we added hydrogen and reach equilibrium. Can I work it backward? Can I take a container and add ammonia, and the ammonia will decompose and give me hydrogen and nitrogen? One more time. You can either start with nitrogen and hydrogen and reach equilibrium, or you start with ammonia and it reaches equilibrium. What will be the equilibrium constant here? You know how to write it? I showed you how. What we have on the right is always on the top. What we have on the left is always on the bottom. Always. You don't have a choice. And we call that equilibrium constant. I'm representing equilibrium constant in terms of concentration. So I put a little letter C. The equilibrium constant is expressed as concentration, molarity. Go back here. Equilibrium constant expressed as concentration. Put a C. So put a C for the first equation, put a C for the second one. You have that on page 6. Page 6, this is part A, write down K4. Page 6, this is part A, write K4, please. Again, page 6, this is part B, write K4. I'm still working with B. How about if I express it in terms of partial pressure? The partial pressure of nitrogen, the partial pressure of hydrogen raised to the power 3, the partial pressure of ammonia. And people say, teacher, what's the relationship between concentration and pressure? If there is more gas, if there is high concentration, of course it will be hitting on the inner wall. We call that pressure. Can I go to part A and put a similar expression? Why did we put it sub P? The concentration expressed in what? Pressure. Let's go here. Can you do part A on your own, young people? K sub P, the pressure of ammonia, raise it to the power 2. The pressure of nitrogen, the pressure of hydrogen, raise it to the power 3. That's part A. So you have choices. You either express it in terms of concentration or express it in terms of pressure. The same to me. I want you to notice something. This is part A, right? Are you there, everybody, or behind? This is part A. What's the relationship between the equation in A and the equation in B? The equation in B. What's the relationship between these two equations? Did you reverse the equation? What happened to K? How is this K different from that K? K is what? In reverse. What's the conclusion? If you reverse the equation, what do you do to K? Inverse. Let's call this part A. Let's call it K sub C and K sub P. Got it? Let's go to part B and let's call this K prime and K prime. What's the relationship between K and K prime? Can I say K is the inverse of K prime? Please notice we have a summary for you on page 6. Summary. It is a general rule. Can you see where we're speaking? It is a general rule that the equilibrium constant expression for the reaction written in one direction is what? The reciprocal of the expression in the reverse direction. That's exactly what we said. If you reverse the equation, what do you do to K? Take the inverse of K. I'm still working on page 6. Number 3. A reaction at equilibrium. If K is very large, let's find K first, then we say large or small. If K is very large, this means what? Is the numerator is large or the denominator is large? What do you say? The top is large or the bottom? Top. This means when the reaction reaches equilibrium, I have more of this. You know what we say? This is how we say it. The position of equilibrium watch this, lies further to the right. This means when equilibrium is established, I have more entropy. That's what they say in the textbook. So don't go out and say, I don't know what she's saying. I'm saying what you have in the textbook. It's an expression telling you when equilibrium is reached, I have more of this guy here, NO2. How about if K is very small? Thank you. Would you kindly write another one? The position of equilibrium lies where? Which means what? When the reaction reaches equilibrium, I had a lot of N2O4. That's what we mean by position lies. Yes?
If you calculate the K in the prime and the inverse,
Yes.
do they have the same equilibrium?
They will be inverse, one inverse of the other.
It would be the same, but
Are you talking about part 2 or part 3?
part 2, like when you're saying that K, if it's large, it lies further to the
Then if you reverse the equation, it will be the opposite.
maybe the upper.
Yes, absolutely right. It's this one, yeah. If you reverse the equation, then K will be the opposite. Yeah. If it is large, you're going to say small. If it's small, you're going to say large. You're very right. You're going to see. We're going to take a lot of examples. Okay, so that's the magnitude of K. One time in the exam, I said, what does the magnitude of K tell me? And some people say, I don't know. It gives you a number. No, not just a number. The number tells you if I have more product or I have more reactant. It's not just a number. Let's do number 4. Page 6, number 4. I really do not know did it reach equilibrium or not. So I had a mixture of A and B and C and D, all of them in the group. Did the reaction reach equilibrium or not? And people, I know you're wondering, what do you mean? Some reactions reach equilibrium right away, in seconds. Some reactions would reach equilibrium after 4 hours. The reaction is so slow, it would reach equilibrium after 4 hours. I'm not exaggerating. There are reactions that take hundreds of years to reach equilibrium. Okay? So, somebody have a mixture and he doesn't know, did the reaction reach equilibrium or not? So what would the person do? The person would put a probe to measure the concentration of A, B, C, D, all of them, to measure concentration. So somebody sticks something, a probe, that probe will measure the concentration. Then the person will establish not K, a Q, similar to K, but K means what? K means we're measuring the concentration when? At equilibrium. At equilibrium. What's the difference between K and Q? K means you're measuring it after it's settled at equilibrium. Q means you're measuring the concentration at any moment. It could be equilibrium or maybe not at equilibrium yet. Concentration measured at any moment. We do not know if it reached equilibrium or not. And we want to find out, is it at equilibrium or is it on its way to equilibrium? Notice I did not put brackets. What did I put? Parentheses. Brackets means what? Concentration at equilibrium. See the difference? Bracket means concentration at equilibrium, and I call it K. This is not at equilibrium. We do not know. Maybe it did reach equilibrium. We do not know. So what do? Calculate Q. Compare Q to the tabulated values of K, for the reaction in the textbook. So you put the probe in, you measure the concentrations of A, B, C, and D. You put the concentrations here and calculate Q. Then what? You open the textbook. In the textbook, we have a big table that has equilibrium constant K for many reactions. So compare what you calculated with what you should have gotten if it had been at equilibrium. So on page 6 at the bottom, if Q is smaller than the expected K, what does that mean? Ready? Q is small. What do you think is small? The top part is small or the bottom? The top part is small. Smaller than what? What I should have at equilibrium. So how should the reaction be proceeding to reach equilibrium? It should be going in which direction? To the right. So I get more of CD, so Q approaches K. So for Q to approach K, must be proceeding to which direction we said? To the right. To reach equilibrium. All reactions, if they are supposed to reach equilibrium, they will reach equilibrium whether I like it or not. It may take 1 day, 1 minute, hundreds of years. If they are on the way to reach equilibrium, they are on the way. The question is, we wanted to know if this reaction already at equilibrium or not yet. So if Q is smaller than what we expect, we know the reaction is on its way. How can we make Q approach K? Remember, Q is small. For Q to become bigger, what do I need? I need more C and D. So the reaction must be proceeding to the right to reach equilibrium. Can you write another statement? If Q is larger than K, this means what? Do I have more of the top or do I have more of the bottom? More of the top. I want to get rid of that C and D. I have so much C and D. So how should the reaction be proceeded? To the left. To get rid of that C and D, I have too much, more than what I need for equilibrium. Would you kindly write another sentence? Write another sentence, guys. And you're going to say what? Instead of right, you're going to say what? Left. How about if Q is equal to K? What do you say? The reaction is at equilibrium. Let's go to page 7.